Today I will present KherveFitting version 1.7. So this is available to download already since the 25th of November. What I want to talk about is done in 11 sections. So a bit about the paper, some downloads, and what is KherveFitting simply, and then all the new features. So let's talk about the downloads on usage. So when you have KherveFitting here open, if you go in the help menu, you have access to the usage stats and the download stats. So if we go in the download stats, we can then see a bubble map, but we have different functions here. So for example, today, this is updated at 12 o'clock. So in half a day, we got around 30 downloads, which is quite good. And if we look at the weekly shows you where how many downloads we tend to get per week. So this line is still linear, so I'm not seeing a maximum yet. So we're around 200 downloads per week, and per month we are around maybe will be around 950, so close to 1,000. The same for usage. So this is in total, since I've put it since September 25th, we have around 5.5k. And today, for example, we have 100 opening. Okay. So let's talk about the themes, because the KherveFitting has changed a bit since last time, since version 1.65, and now you have a menu where you can change your styles, and especially it's very good for the changing of tabulation. So for example, the grid layout, I can go to tab like this and side by side. So side by side is the way it used to be. But I found that it doesn't provide enough space for the peak fitting. So I rather put the results grid and not see the data of the results grid, and I rather put it on the right side. So that's what I do in here. I put it on the tab, and now my results grid is here. And obviously I can change the look. So this is how it used to look before, with no styles. But right now I prefer the dark mode. You can choose and check the others if you like. So what is KherveFitting? So KherveFitting is an XPS fitting software, and it's usually downloaded or installed into the desktop. So this is his folder. So you get the executable, that shortcut in here. And we get a backup folder, data example folder, on a peak library. And then it's got a different database that allow him to know what it will be fitting. So that's how it's looked for now. And let me show you a basic example. So if I go to File, I will start the example menu, which is in the example folder. And I'll go into Carbon and, for example, Carbon SP3. So right now, I only want to fit this to show you. So for that, we will use the peak fitting model window. And this is the advanced one. There is also a less advanced one, which is this one here, for beginners, where only the required buttons are available. So for background, 4 buttons, and for peak fitting, 4 buttons, and that's it. But for the sake of this video, I will show you with the advanced one. So when you open, you have 3 tabs: the background tab, the peak fitting tab, and the batching tab. And in the background tab, we have 2 red lines. And if we create the regions, we get in the smart mode, we get a background, and we can zoom into the background using this. And then we can adjust our background. So let's just move it somewhere here, and this is quite nice. But just to show you, if I use my shift key, so I press it right now, and I can then move this. So I tend to put it around there. And then this one I may just slightly change. You have an average, as you can see from those amount, but I'll still change it around here. So now I can zoom out using this right click and then zoom out button. And now I can go into peak fitting. So this is a standard spectra for an adventitious carbon, and it is usually made of 4 peaks. So it's a 1s, so it should not be doublet but singlet. So I will create one, which is my CC peak. I'll create a second one. It goes to the maximum, and then I'll use my tab key or click here or click there, and then I can take it and move it down there. Okay, and I will do the same now, and I'll use my tab key and I'll move it somewhere here because this is C double bond O, and then I'll use the next one, which is OC double bond O. So just to make sure I know what I'm doing, I'm going to call them already what I believe they are. And this is standard things. So C single bond O, and then C double bond O. And I must keep the label carbon 1s because the program will look in the database and look for the sensitivity factor. So for carbon 1s, the sensitivity factor is 1 because it's been referenced to 1. Most of the time. It can be referenced to fluorine 1s, but in this case, that's what it will be. And then the rule of thumb is to make the same width and shape, which is in here, the full width self maximum, the LG ratio, and I'm going to make it in function of A. So I'm going to type A, and I'm going to do the same on all peaks, except obviously peak A. Okay, and then I fit n times. And if it's not done well, which is, okay, it's done quite well actually, it found itself back. And this is coming at 1.12, and we have a good binding energy position for the CC. And the next feature I want to show you is the introduction of heat map. Okay, so here I have a file made of 42 elements. And it's the file that I tend to use for my workshops. So a very important icon is this one, the sample manager. And the sample manager obviously is very big because I use a lot of different things. So let me just put it to what we need to do. Okay. So right now, if I just use my control bracket, I can then follow the different things. So this is the one I wanted to look. So I go from carbon 1s, 1s evolution, yeah, and I've got different up from 3 to 7. And you can see that there is an increase. Okay, and the last one has been fitted. So first you can, as usual, using this this file manager, you can plot them in different all together. You can also offset them using this one or F3, and if they were fitted, you could plot them, and you can see the fit here. Okay, the different colors, you may not be happy with the color. You can change all this now, right clicking, and the multiplot settings are here. And this, once you've changed it, it's saved in the config file, so you should not have you should go back to the standard. So for example, if I use rainbow, you get this nice color. Or if I use a color palette gradient, purple for example, it's also quite nice. So different gradient. But by default, because KherveFitting is green, I will continue with green. So here, what I want to show is here we can see an evolution. And we can now plot it using this map, and we can still use this down in there, and we can just have different intensity, and obviously using the control down button, yeah. And the same, we have different color palette. Now we have the heat map palette, and we can make it let me just go to something nice, plasma maybe, and anything you want. Really. Okay, so this is a nice addition. Now I will show you batching, something that was introduced before, but in case people have not seen this before. So for example, here we have some pigs that have not been, or some coilovers that have not been fitted. Yeah. So if I go to carbon 1.7 and I want to fit those ones, I can easily now go, and let me just put that down there. We don't need to see it for now. I'm going back to my pig fitting. And so what I can do is use that batching. And that batching, if I unselect them all, and it was from 3, 4, 5, 6, and not 7, we've done it before. What I can do is I first can propagate the pig fitting. I've done so. I can then fit the rest. So let me just change the number of iterations. I think with 5 will be enough. And I can fit them. And that was quite quick. So please do not comment on the pig fitting. It's not about the pig fitting in this case. It's about using the software. So those I have created some. It may not be correct, but it's an example to show you the capability of the software. So now we have fitted in few seconds those files. And what we can go back now, we are happy with it, let's say. Maybe not here, but let's say we are happy with it. Obviously we can replot it like this, and we can now plot it using this stack fitted plot, and you can see them all nicely fitted, and that's it. This is the batching. So my next feature that I have not mentioned before, but this came in 1.65, you may not have realized was there, is in this measure area. So this measure area also has a batching, and so together with the profile, we can basically create a depth profile of any surveys that we have. So let me show you what happened here. So in here, first I had a survey that I've analyzed using the automatic ID that I had here. And then I've optimized like I wanted. And I created a batching where I propagated the area to all the numbers I have here. So my sample in this case, it's a combination, it's multiple thin films. So it's a niobium nitride and titanium nitride, so provided by Ryan Bauer. And basically, what we get is we get 10 nanometers of niobium nitride, 10 nanometers of titanium nitride, which we don't see here because it's the beginning. And then it's been deposited on silicon oxide. So what happened now, if I just go from 1 to 1, you're going to see what happened. So it goes slowly, and then we can see the titanium coming here and increasing straight, and the niobium will go down. So this one will go down, and then the nitrogen kind of stay the same. The oxygen completely disappeared for now because we are no more at the surface. So we go from 1, and then it's niobium's coming back. As you can see here, titanium is going down. So now I'm showing like this. You can see basically what's happening. We go from one thin film to another thin film, and then we come at the end, we are coming to the silicon oxide. So this is silicon 2p, silicon 2s, and we are seeing the oxide from here. And then next one, silicon oxide is more obvious. And again, yeah, now we can see a very strong silicon 2p, silicon 2s. The oxygen stayed the same, but actually it's decreasing now because we are going to the metallic silicon. Okay, so another way of presenting this, we go back to the sample manager. We can click them all and we can plot. That is obviously not too obvious. Let's try to stack plot. We can see things are happening. But now if you use the heat map, then let me just decrease my heat map. Okay, so if we use the heat map, you can see from number 1, or those ones, we get niobium here and titanium here. So niobium 3D, titanium 2P, and then at 400 is our nitrogen, which is constant. So what we can see is we have a constant decrease and increase of titanium or niobium until we come to layer 42, where silicon 2s and 2p are shown here. Okay, and we have at 530, this is the oxygen 1s, we can see it appearing there. So again, this is the heat map is quite nice. Let me just show you with another, just to show you it exists. Qualitative, I'm not too sure what I should use. Maybe seismic, yeah. Okay, so this is even more obvious now. And so what can we do with this? Well, we can do a depth profile. So we can simply go into our profile window and we can select all of them, all the survey, yeah, and they are already maybe PCA done, no, okay, then we can create a profile again from PickFitting, because in our results we have nothing, so it's from the PickFitting grid for surveys. And if we do that, and maybe we don't want the very first one, let me just remove the very first one, we don't want to see the dirt, so something around, it looks like it's really starting around 5, 6, yeah? So I'm just, that's it. Now I'm creating the profile, so it's going through all of them, like that. And then it's thinking a bit, and we have the profile created. And so what we see is the niobium 3D shown here, and the titanium 2P shown here. It's a bit wrong at the beginning. I think it's really start up to maybe the layer 10 or the sputter 10. And basically now we see an increase, decrease, increase, decrease of both, almost a constant for nitrogen. And then you can see in green is the oxygen 1s. We have an increase, rapid increase when we come to the silicon oxide, and then it quickly decrease. And this is our silicon metal. The next feature I want to show you is really new now. So those are the creations of single entity. Sometimes in spectrums we tend to fit peaks to just fit the envelope, and this is very true for manganese, iron, chromium, and nickel, and so on. So I'll show you in one of the examples, and I'll go to chromium, for example. So in here we have the chromium 2P, and the chromium 2P shown here is made currently of 7 files. 7 core levels. So right now we have 5 picks for chromium 3 plus. Oh yeah, chromium 3 plus. And then we have 1 pick, asymmetric pick for chromium 0. Then we have another pick, which is this brown one, very broad, for chromium OH. So let's say you want to create something about the chromium 3 plus. We could simply delete for now. So let's delete those picks, maybe just those ones. And what I can do is I can create this feature as a single entity now. So what I can do is I can go to save, and I can create a single entity using pick model. So let me just name that. So I've already created some tests, but let me go to test 4 this time. And that's it, it's created. So what does it do? Well, when you go now to library, we can go back to test 4. And first, it creates like a pick model. So usually we can add or we can override. Let's override this time. So before we had 5 picks. Now we override that and we get the same shape, but as and let me just try to move. So we can only move the pick if we go to pick fitting tab. So now we can move it, and so that way you can create different oxidation state as a single entity, and instead of having 15, 16, 20 peaks, you get 3 peaks. Okay, so for example, I could continue, do the same. I go back to the metallic one. Okay, I'm going to override this, or maybe not this one actually. Let me cancel this. I'm going to go to something much harder. So let's say I had nickel chromium 204, and so I'm going to override this one. So this is made again of 5 picks, and I'm just going to move it slightly bigger, and I've just moved everything, but it's all in function of A. And now you could save this as a single entity, and this would be test, which one? Test 5. Okay, and now I could call first test 5. Sorry, this is on my way. Okay, test 5. I'm going to overwrite what I have. So this is the one, and now I can add my previous one, test 4, and so I have 2, and I add that after. So I have 2 entities, and let's say I could fit this, and obviously it's not going to fit because I don't have that, but you can quite understand what I'm trying to do here. Okay, I think I have fitted the carbon. So for example, I will show you with an entity. So I'm just going to try to remove one, the CO, this one, delete pick C. I'm now going to save this one as an entity. Maybe let me just this time put it down there. I'll call it test 6. Okay, and then what happened now is if I call it, sorry, this I keep forgetting to take it off, overwrite. Now I get a single entity again, and so I will show you some, because that should fit now. And if I add a simple one here, and I try to fit it, you can see now it was much quicker to fit. Obviously in here it's not shown here because we have one word. Yeah, you have to call it something, carbon 1s and space, so 2 words will show something. So if I do P1 or feature, then it will show feature. Yeah, if I just remove the word, maybe I put them together, this word, then it won't show into the legend like this, it won't show up. Yeah, so that's what happened, but it really improved the speed. If you have 20 picks, that's really the way. The next feature I want to show you is the introduction of principal component analysis to KherveFitting. So this is the one I like the most, and I have selected a sample or a set of experiments done by Mark Isaacs. There's a paper that is created already, and he has given me those files for the KherveFitting paper that was released today. And here I have a selection of 51 files. So you can see them all here. And so what I can do is I can select them all. And maybe let me go from here. Maybe, yeah, okay, all of them. So I'll select them all in here. Plus, I'm going to remove this one. And now if I just put them all together, what you can see is, I mean, first they look all the same, except we can see an increase of the cerium 3+. If you know about cerium 3D, you know that this is the satellite of cerium 3+, and right here there is a full cerium 3+. So if I put it as an offset, you're going to see slightly more. So we have the 52 of them plus a cerium 3+. And that's nice. We need to have some nice core levels that we believe are the ones we want to get through from the PCA. And if we don't have them, then it's a bit difficult for the PCA to find what we want. Okay, so, and then here is some data that I already got from this, but let me just continue. So this is the data I want to analyze, and what he found is through X-ray, by the way, is that there is an increase of serum 3+. Yeah, so this is the X-ray that creates the serum 3+ into the serum oxide. And so now I go into this PCA and I get this window, and then we can, like all the other things, we have the select all, and we can right click and select all the serum 3D, which I can do right now, and we get them all. Plus there is also a very nice serum 4+, more or less, and we can use it. Yeah, fine. And we can create a smart background if we want. We can do it by height. We can avoid using this and they just look like that. But let's just use the max height. And then we can look at how many components we want. Usually, you will tend to choose the minimum components. And it will work better if you don't have that many components. So luckily for cerium, we are looking at 2 components, the serum 4+ and the serum 3+. If you were on iron, you would look maybe for 3 components, 2 for the iron 2+, 3+, and 4+, and that may be more difficult. So now we analyze that, and it doesn't matter if the data is not the same size, it just go and find the minimum size. Then we analyze, and straight in 1 second, first we get the very nice looking serum 3+ in here, so he found those 2 components, and then also a nice serum 4+, and he's plotted the amount of serum 3+ to 4+ on the right side. And at the end, obviously it went crazy because we have full serum 3+ and full serum 4+ in here. Okay, so if I now, or not full, as full as we can, and we can just zoom into that. So let me just remove this auto axis, go to 30 and 70 maybe, and that should show us that there is an increase of serum 3+ in here, and then it's stable. So after the plot number 10, we have a stable serum amount of serum 3+ into our spectrum. So what can we do with this? First we can, and if I just show this one here, first we can export or create PCA as core levels. So those are the 2 there, which I've done before. And also you can fit, or you can add those ones as single entity components inside each of them. So for example, if I now go into the first one, okay, so that went straight. Okay, let me just double click and I will just show you. So this is the first one, and if I press, and now I have 2 of them, so let me just put that away. You can see what I mean. So now we have the add PCA to core levels, and so you will go through the 51 spectrums and you will add the single entity. Okay, so this happened to all the spectrums. So if I go now to cerium 3D1, we can see them here, and so that was quite quick. And we have in here, we can have the create, like I said, and this is the one shown here. Okay, a single entity. So what can you do with this? Okay, so let me just remove this. Obviously, just one thing, if we can click on 3, we should get something that we don't expect. You really have to know what you want to look for. So here it's definitely not 3 components. It didn't look right, but using those 3, we will fit all those spectrum. That's what it really says. Okay, so you have to know what you're doing a bit when you do PCA. So now, for example, what would you do with this? I can go to cerium 3D, let's say. I get this gibberish thing, and for example, what he did is he created an offset, he created a background which is called offset, so just a 0. Okay, and then we can now fit those two single entities, so they are single entities spectrum. Let me just show you this. They are maybe okay, so from there, single entity fitting model, so I click on this one. Let me just remove that, and now I could fit this. So let's say 20 times for the first one. You can see straight it was done almost in one go. It looks like it's fitted okay, and it may not have been fitting okay, and I will explain why. It's because we've done the PCA, and when we did the PCA, one of them was a different dimension than the rest, so that was this one. So you see 865 here, and as far as I know, it is not done for this one, so it goes to 870. Okay, so what you have to do then is, let's say you come here and we can change, let's say the go to 870, and we can change that, and maybe it will fit better, slightly better, if we just change the background. So now we could basically propagate this, but now I will just try to fit them all using maybe less iterations, so something like 4 iterations, and I will try to fit only the cerium. So let me remove all those ones, and I can fit the selected, and now you can see how quickly this fit. Okay, so we have now fitted 8, and it will continue like this throughout the whole lot. So now the fitting is done for the 52 of them. And basically, if you continue, so I'm going to use my control left bracket to go in between like that. Let me just go quickly, and you can see them just being done nicely, yeah? Like that. So using this, we can find the concentration, but obviously the background wasn't created. There is no Tugar background yet that I have added. But it's a very good indication on how much there is from cerium 3 plus to 4 plus. So you can think we can afterwards create a profile. So we could use this profile window that is here and select all the ones from Ceria. So let's say right click again, all cerium 3D. I may not choose the 2 of them that we know are the pure one. And you can create a profile from those peak fitting grids. So we have the results grid here, so it's not going to be that. So we go to this one. And now it's going through them all and create a profile. We're at number 45, 50, so very soon. Okay, so now we get something similar to the data we've done on the PCA. And we get around 32% of this single entity component, so we can see an increase. Whether this value is correct, this is at least my first attempt to PCA, so I will later on add a Tugar, and maybe that will become more and more true. So the next feature I want to talk about is this KherveDB. So the KherveDB is this question mark BE icon. So when you click on it, you get a periodic table looking like this. And on the side, so let me just try to make it bigger. Like that. So in total for carbon 1s, we find 5,900 elements. So this is an offline NIST library, and you can actually search on it. It's by default on carbon, but it can be on any of them. So for example, if I look for SiC, silicon carbide, I have it open here, yes, and I get 80 results. So I can further look in my search name, and now just getting the silicon carbon. So 78 results I can plot, and I can do a plot of the amount of reference, and that tells me that the binding energy should be around 283.4.5, yeah, or 0.3. So this button allows us to go into other database. It's basically a web page, but a web page which I have selected the best example. So let me just try to give him more space so we see a bit more. Okay, so for example, all those web page up to here, so XPS Fitting by Mark Bissinger, Harwell XPS by Harwell, the Guru page, and then the Knowledge by Thermo, they are all in function of the periodic table. So for example, if we have carbon, you can see them all shown here, and this is a very nicely database or help website done by Mark, and the same for carbon. This is the newly made by Mark Isaac at Harwell, and it's got many new features that I use, so it's quite different to XPS Fitting, and I find it complementary. So I really advise it to go first to Fitting and then Harwell and continue like this. So for new users, I recommend to use Thermo because, for example, when you have 6,000 data that we saw for carbon in here in the NIST, in there we only have 4 or 3. So it's not many. It does help. It's not overwhelming, but it's not enough. So XPS Fitting on Harwell are really the one I recommend. So what I was saying is, for example, this is carbon, and if we select titanium, now the page on all those pages are for titanium. So it's very nice. It's a web page or website led controlled by this periodic table. Okay, so this is empty simply because I'm looking at carbide on silicon carbon, and now you can see 754 results. So I really recommend it. And again, I also recommend Mark Bissinger website. So the next pages are different, but I will call, especially this one, I will call it the database of data file. So it is simply Google Scholar, but specifically looking at surface sound spectra. So for example, and you should not search into the Google Scholar, you should go into the search here, and you do simply, for example, I'm going to look at copper 2O, press enter or search here, and now I'm coming to Google Scholar on surface sound spectra, and why is it good? Because when you go here, you go straight to the website of surface sound spectra, but you can go down and you can go to the supplementary material, and that you can download, which we've just done. And when you download and decompress to remove the zip, I will show you what happened then. Remove the zip, you can then you end up with this, and that are ASCII file. So we have 5 ASCII file, and you can select them all, put it into the plot, and KherveFitting will understand what he needs to do, and he convert them into an Excel file shown here on a JSON. So next bit we can do is we can recreate this one as a standard file. So like call wide. We can then go into for copper, we can call it copper 2O or copper 2P, sorry, because it's the core level we're after, and we can continue like this, like oxygen 1s. So now you understand what I mean by the database of data file. Obviously, if you use those ones, you have to cite the author. In this case, it was Vasquez. Okay, so the next thing I want to show, so let me just go back to the periodic table. So the periodic table again, we did not finish on the last one, is the good paper scholar. It will be a bit laughable for the experienced XPS user, but for the new users, I find that they do not find the correct paper. So This, all it does on Scholar, I just put electronic structure in front. And so, for example, if I go to CeO2, so cerium oxide, and I click, I get straight away the very nice work from on well cited, and there I will find some very good example. Okay. And then I have, as the last tab, it's a tab with all the PDF that I think are useful, and for especially the new users to read. So this, and unfortunately it does, you have to click on close here, and let me see if, yeah, okay. So it's the explanation of the multiplet splitting by Mark Isaacs, and the Coster-Chronic effect also by Mark, the deep parameter by David Morgan, which I use for SP2. Then we come to the 3 papers which are very important from Mark Bissinger, and where I found all the pick table which are inside the library. Okay, so the rest is done. So now I will show you, for example, using this wide, the next feature which I've improved. So this is the manual identification, which I found that several people use. So it's slightly big, but it provides an easy way to know what this is. So for example, we obviously look for copper, and we find this is copper 2p, 2s is seen here, 3p, 3s. Then we are going to look for carbon, yes, and oxygen. So this is a nice way to find. Unfortunately, I did not add the Auger. It's been a miss. I will add it to the next version. But what I have here is this ID by range. So for example, if I now zoom into carbon, and I look at maybe something that I have, I don't. Let me just move that somewhere there. And now I have several picks, and I can just go ID by range, and it goes straight at the center, and it shows us all the elements that are supposedly here. Obviously, some are unticked because otherwise it's too many, and we can see. So in red are the most commonly element. Okay, so if you tick it, all the rest are going to be removed, but they're always there. Okay, and because they are in these element groups, you can untick the one you don't want to have. And you can see now ruthenium 3D and others. So it's the intensity is as per sensitivity factor, and so osmium 4D is the most sensitive, so that's why the others are kind of relative to it. But obviously osmium is not something that we expect often. But now we have here, we have so-called the strontium, we have the, we should have maybe the copper 3s, and that's the one we are after. So shown here, copper 3s, and so on and so on, okay? So that seems to be zinc maybe. I think it's zinc 3s or PB4F, one of those. So the next feature I want to show you is the addition of the NPL transmission. And this is more for advanced users, people who have calibrated the XPS machine using the website from NPL, where you can send your VAMAS files of copper, silver, gold, and you get a calibrated, even a certificate by NPL, and they provide you with the transmission function. So this is for now available on VAMAS, on Casa XPS, and so it comes as a VAMAS file. And so I have here a VAMAS file that was provided by Alex at NPL. And what you do, so let me just go back to at least a good view of this. Let me just put that nicely. Sorry. F2, yeah, it looks good like that, maybe, yeah. So If you do that, usually you would tend to go where the instrument settings is. So you go to Edit Preference or into that gearbox here. The gearbox gives you all the settings that are available in KherveFitting. Then you would go into Instrument Settings. Instrument settings give you current instruments, so all the different database that I'm using. In this case, if you use the NPL, you want to go to the AMRSF. So this is the relative sensitivity factor that are general and that are absolutely true. For that, you would want to go to NPL method, and then you would want to go into this icon. So this icon is where you can add some cross-section. So let me just add that here. And you have a choice of 3. So right now I have added only 1. And you can see that you can get some of the data or some of the value here. And you can go to the next, and it wasn't done. So what you get is those values, A0 up to A4, B1 up to B4. And then what you can do with this is you can add this transmission into the Excel file. And inside the Excel file, then it will correct the data by itself. And then you can use the standard, and I just put it down there, the standard OIMRSF. And so this provides both, because NPL method is 1, that's what it is. And so you don't need to use TPP2M, you just use that. So just to show you how you do it, you can, for example, go to NPL narrow, you could look for the VAMAS file, or simply, let me go, can't really do that here, so let me just put that down there. That's it. Okay, so in here, simply what you can do is take the VAMAS file and drag it in this location. Drop NPL VAMAS file here, and that straight goes in here. So you get from the VAMAS file. Okay, there is an OK to do. From the VAMAS file, it gets all the A1 and so on, and now we get the transmission function. So I think it's quite a nice addition. I find it much simpler to see than Kazaa, because I don't understand where it goes and if it really went in, where this, I'm absolutely sure that this went in. The last feature I want to show you is that we can fit a XAS sample. So I was asked by people at Imperial to make it available in this, because they believe that it does not work well with the other software that they've used. So it's really a new addition from this week. And basically what it is we have an import here, and right now it's an import of a text file, and that's only for B07. But if I get B07, that's synchrotron diamond. But if I get different files, I can add more type of XAS samples in here, and that's basically the data is looking like that. And we know that we want the third column in here, and the third column is negative, and it's also in nano count here, 10 to minus 9. So for KherveFitting, we have to have, because in XPS we have usually millions of counts, so all we have to do is we have to multiply this. So this import will do that for us. So let me just go into this import and find the data. Maybe I'll just open one that I've done before. So let me just go into a recent file. But basically we get something like this. And so what we have, and I could have fit this as well, is we get the, in this time, the cobalt LH. So let me just remove all regions and all peaks to show you how we do it. So instead of going to the standard smart background, we would go into the Arctan XAS. Okay, and I've included XAS so you can know what it is. And then we are going to do an Arctan type background. So we can go down into the background, yeah, using this one. Let me just quickly go to another one. That's it. So we can go down into the background in here and create a region, and then we get something like this. I mean, it's not perfect. This is the arctan, so somehow it cuts. The arctan is cut, but you can use the offset now, yeah. And so if we use the offset, we can go down and do something like this, and we can only go up to here. So it's it looks like it's not enough, but actually when you look at the data itself, it's really close. Okay, so this is a standard, maybe just going through there. And so you can now create a new region. Let's say if you think only 2 regions are required, you can do more regions if you want. But let's say we create a second region, so we click on this button, we make a new region here, and that comes with different values. So let's just move that down, something very close, and maybe further up here, and that's how we do this one. And now we could, let's say, fit this one and fit this one. So let's say we go to add single pick, add another pick, so it's going to go to the maximum, and I'm just going to create picks to create picks. It's meaningless, but it's to show you that it is possible now on KherveFitting to fit XAS.